Hi everyone! In this episode we'll look at new functions in our database tool. Database tool is a program we are developing in the LabVIEW environment, and our goal here is to bring together all possible database operations such as open databases, find all databases, select the active database, database in use, save the database path, save path, encrypt this path, encryption, as well as database interaction functions such as display database tables, automatically resize the table on the user interface, auto-size, search the database by various criteria, database search, sort displayed values by different criteria, sort by column, save displayed values to a file, save txt, view table size and other properties, view size, insert and replace cell values, insert record and replace cell, delete values, delete record, create and delete table, perform arithmetic operations on numeric values in a table for a single cell or an entire column, multiply by column or cell, create additional columns, create and add columns, and delete unnecessary columns, delete columns. We also continuously display the number of columns and the number of rows shown in the table on our graphical user interface. We have already covered most of these functions and know how to program them. We also know how to implement system login and create passwords for both the operator and the administrator. We have reviewed the differences between the operator user interface and the admin user interface, meaning the operator doesn't have access to all the functions available to the administrator. We already know how to implement all of this. In the previous episode, we began working on automatic table creation, and I decided to enhance our database tool by adding the ability to connect peripheral devices and record values from these devices into our database in real time. Last time, we looked at the fetch data capability using an ARM microcontroller. This microcontroller is part of the USB device manufactured by National Instruments. It's called an USB 6008. To work with these peripheral devices, we created a fetch button as well as an index window. By index, we mean a specific data stream that is coming into the various inputs of our USB 6008 device. Today we will look at how to program the Cortex microcontroller located on the Portenta H7 board using our application. You may also be wondering about the robot you see in the left corner of my screen. As we all know, artificial intelligence and various bots, such as ChatGPT, are very much trending right now and position themselves as AI providers. So I thought, why not create an artificial intelligence that works together with my database tool? For example, why not make my database tool respond to voice commands, automatically pull the required information from the internet, create tables on its own, and in general perform tasks that an AI system is expected to do? Maybe I can build an AI that will do my work without my direct involvement. Don't believe I can do this in a single lesson without using bots like ChatGPT? Well, let's watch this video to the end and see what happens. So, let's begin with the next function we want to study today. This is perhaps one of the key functions when working with databases: table creation. Right now, I'm logging into the system as an administrator. First, I will create a table as a user, and then we will look at it from the programmer's perspective. I open database number 1, and here I will create a customer database table and name it customers. So, why does table creation seem simple at first glance, but in reality is not such a trivial task? Let's look at the table from this perspective. A table itself carries meaning. The correct naming of columns is part of the business architecture. In other words, if you run a certain activity, it is always associated with a set of important and significant parameters. When creating a table, you must take all these possible parameters into account for your specific domain and plan for many years ahead. You need to try to forecast how your activity may evolve, what new directions may appear, and what may lose relevance over time. Therefore, proper table design, considering all factors, can not only organize your data but also create a direction or vector for the development of your business. To create a table, I have provided a window where I enter the table name and the Create Table button. I also added a Cancel button in case something goes wrong, and a Delete Table button if I later decide the table is no longer needed. I type customers into the table creation field, and now the column configuration appears, which I will fill in now. Since this is customer information, I will need the following columns. Customer ID, this will be my internal customer number sequentially assigned. The second column will be name ID. The third column will be address. The next column is phone, and the next is email. There are many additional factors that could be considered here, but our current goal is not to service a specific business, but to demonstrate table creation. So I will add 2 more columns and stop there. The last columns will be approved by and timestamp ID. Since there are certain constraints when naming columns, meaning some words are reserved and cannot be used, and we discussed this earlier, I added _ID to almost every column name to avoid conflicts with database rules. Since we initially decided that our database will use the string type, I mentioned this before, I keep string everywhere, although other options are available. As you can see, we also have long, single, double, datetime binary. I will set the field sizes as follows. First column 10, name ID 100, address 100, phone, I think 20 is enough, email, let's say 30, approved by 30, and timestamp ID 50. I also enable null for every column. Allow null, meaning empty cells are permitted. Next, I press the Create button. A confirmation dialog appears. OK. The table is created. We programmed it so that the newly created table automatically appears on the user interface. Now we will look at how this is implemented on the programming level. But first, I will fill several cells in my table with random values to make sure the table works. In the first cell, I will have numbers. In the second cell, numbers and letters. In cells 3, 4, 5, 6, also numbers and letters. Now I press Insert Record, the data is inserted, and the newly added data is highlighted in green. Now let's see how this looks at the program level. I stop the program, power off, and go to the block diagram. But I will do it deliberately. I will locate the terminal of the window where the table name is created and immediately jump to the loop that performs my task. Database table name to create. What do we see here? We see the data flow passing through the functions. Let's analyze our data flow. So, the table name is passed into our sub-VI called Remove Non-Alpha Characters. Let's take a look at how this sub-VI works. Here we can see that using this logic, we filter the incoming value, the table name, and allow only uppercase letters, lowercase letters, numbers, and underscore. It's important to know that when creating a table name, numbers can appear anywhere. However, when naming a column, the column name cannot start with a number. Next, we check whether this name already exists in the database. To do this, we use a for loop, feed it a 1D array of all existing table names, and compare them one by one. If a matching name already exists, we go to case true, where an error message appears. This database table exists. Then, through the enum case, wait for event, we transition to the timeout event case. Also, and I almost forgot to mention, there is another validation. If the operator attempts to create a table without a name, we use the empty string path function. In this case, the first case triggers and the error message appears 1 character min. And then again, through the enum case, wait for event, we return to the timeout case. So we currently have 2 validations. Of course, we could add more conditions, but I implemented 2. If both conditions are met, we proceed to the case disable controls for database table name to create. And at the same time, database table column information becomes visible. Here, in the case disable controls for database table name to create, after we transition further, we execute our standard logic. We disable the buttons that are not needed during table creation. Why do we do this? So that the operator doesn't accidentally trigger some function that is incompatible with table creation. Next, through the enum case wait for event, we move to timeout. Wait for event, timeout, and it is exactly at this moment that we get the ability to fill in the characteristics of our table. This is the part we just filled out together. Since we are already here in the case db table column information, let's look at the logic. This event case executes whenever any of the values in the table definition form changes. For example, when we enter a column name, it is automatically validated through the sub-vi remove non-alpha characters. The same applies to the column size. We protect the user from mistakes by allowing the cell size to be formatted only within the range 1 to 255. Of course, we could add additional validations here, but I proceed from the assumption that the operator has a basic understanding of what is allowed and what is not when creating a table. In any case, if the operator makes an error, the table simply will not be created. Thus, once we have defined the table characteristics, we are ready to save it. For this purpose, we use the Create Table button. Let's see how it works. I locate the terminal of this button and jump to the db Create Table case. As usual, the program executes from left to right. First, we display a dialog asking the operator to confirm table creation. After confirmation, we enter case true, where we create the table, clear the cells of our table on the user interface, restore the default colors, and make db table column information invisible, since it's no longer needed. The table itself is created inside the db create table sub-vi. Let's look at its logic. Here we see our standard workflow when using the database connectivity toolkit. Before executing it, I added 3 additional checks. If at least one of these 3 conditions is not met, the main logic will not run and an error message will be shown instead. In the first case, the error message will be database table name exists. So this case becomes true if we enter the table name that already exists. The second case triggers if table column information is empty. The third case triggers if the table name field is empty. Thus, if all 3 conditions are met, we execute the following logic using the database connectivity toolkit. We open the database using dbtools open connection. We create a table using dbtools create table. Then we use dbtools list tables to output the list of tables. Here it is important to note that we sort the table list using the MGI natural sort function and add an empty row at the top of the database tables window. Next, we use dbtools list columns to output column information, and then we send a short SQL command to return the top 1000 rows from our table. Even though we know the table is empty, I kept this function because it is followed by our standard procedure to display the table values on the monitor. We already covered this in detail in previous episodes. So here we have created the table. I close this sub-vi. After execution, we move to the case enable controls for db create table, where we make our buttons active again. Let's also briefly look at the cancel and delete table buttons. In the DB create table cancel case, we reset the values of our variables, clear the table, and make all buttons active again. That is, we transition to the case enable controls for DB create table cancel. Here I think everything is clear. Now let's find the terminal of the delete table button. Here I implemented two conditions. The first check is the presence of a table name in the DB tables window. And the second is operator confirmation authorizing the deletion of this table. For deletion, we move to the sub-VI db delete db table. Let's see how it works. Here we see the database connectivity toolkit in action. The table is deleted using the dbtools drop table function. All the remaining programming flow we have just reviewed, so we can consider the table creation topic complete. In the next episode, we will look at the mathematical operations on cells and creating columns. And now, as I promised, we will program another peripheral device, the Cortex microcontroller. I will close our dbtool project. We won't need it anymore today. And a few words about our microcontroller. The Cortex M7 480 MHz is one of the fastest microcontrollers available today. It can be integrated into virtually any application because it offers a large number of analog and digital inputs and outputs. You can always find more detailed information on your own, but for now we will simply program it using our software. This is an add-on created by the TS Experts group at Aladdin Engineering, Arduino-compatible compiler for LabVIEW. I will not go into detail about how we obtained and installed it. If you run into installation issues, write in the comments. Now let's move on to programming. You'll see how simple and easy it is when using our programming tool. I open the folder where my programs are stored. I have prepared two sketches. In the first program, we will make an RGB LED blink, blinking of the red, green, blue LED. In the second, we will connect our light sensor, which we already reviewed in the previous episode, to read data for recording into the database. Here we see the pin diagram of our board. We will use digital pins 14, 13, and 12. Here's the Portenta in the box, the one you saw on the screen. I take the Portenta out. I also have a Wi-Fi antenna here. I won't go into that right now. If anyone is interested in how to use Wi-Fi with this board, let me know in the comments. Now I connect the Portenta to the USB cable. Let's connect it. As we heard, the computer detected that we connected something. You may not have heard it, but I did. The computer definitely recognized the new device. Let's see what exactly was connected. To do this, I open Control Panel, Devices and Printers. And we can see that a new device has appeared called Envy. To make this device bootable, that is, so we can upload firmware, we need to activate boot mode. Right now, our board is running some existing task. We don't know what it is, but we will create our own. To activate boot mode, we need to press the reset button twice here, in the center of the board. Now the green LED has started blinking. As we can see, the Envy device has turned into Portenta H7. In the device properties, we need to check which port it is using. It is on COM5. Let's remember that. I close the control panel. We won't need it anymore. Next, I open the block diagram of our program. Where do we get these functions? In the Arduino compiler package, we have a set of functions located under add-ons, Arduino compatible. Here they all are. They are written in C++ and presented as icons in our program, which makes them very convenient and easy to understand. Using these low-level functions, we can program our microcontroller. Now I'll quickly go through these functions. Structures. These are the familiar structures that help organize the execution flow and program logic. Array. Functions for working with data arrays. Creating, indexing, resizing, and modifying arrays. Numeric. Numerical operations such as addition, subtraction, multiplication, division, and so on. Boolean. Logical operations used for decision-making and state control based on true-false conditions. String. Everything related to building, parsing, concatenating, and analyzing strings. Timing. Delay functions, stopwatch, timers. They control time intervals and task synchronization. Trigonometric. Trigonometric functions. Utilities. Helper blocks that extend program capabilities. Analog. Functions for reading and writing analog signals from various devices. Digital. Allows you to read or write digital signals on Arduino pins and control switches, buttons, and other digital devices. Interrupts. Allow handling asynchronous events, button presses, sensor signals, by calling LabVIEW-like functions at the moment the event occurs. Tones. Sound signal functions. I2C LCD. Functions for working with LCD displays over the I2C. Serial. Serial data communication. And next, compilation. Compilation tools. RGB LED strip, a set of functions for controlling RGB LEDs. SD card, functions for working with SD cards connected to Arduino. SPI, everything related to the SPI. I2C, functions for interacting with peripherals via the I2C. Servo, functions for controlling servo motors commonly used in robotics. So, return to our block diagram. Here we see a while loop that runs continuously and a set of functions that execute sequentially from left to right. By default, before the program runs, we assign the terminal rows. In this case, all digital pins are configured as outputs. As I mentioned earlier, we will use 3 pins. One for the red LED, one for the green LED, and one for the blue LED. We will make them blink within a period of half a second. I think the block diagram clearly shows how it should work. And yes, before connecting real LEDs, I'm currently using the LEDs on the board itself. I have a reference here. I set the red LED to digital output 23, the green to 24, and the blue to 25. And now let's save it. Next, I go to the control panel of my application. Here I need to make sure that my board is connected. I know it should be on COM5, so I go to Tools, Port, Detect Ports. Now we see that port 5 is selected and our Arduino Portenta H7 appears in the list. We can confirm that the Portenta is on COM5, and in the lower corner of the user interface we can also see that everything is connected correctly. I start the compilation and firmware download, compile and download. Watch the Portenta, I'm holding it in my hand. Let's see what's gonna happen. As you can see, the LEDs are blinking. The program shows an error, but I'm not going to investigate it right now. It's most likely related to memory allocation. What matters is that the program works. Now we'll connect real LEDs. I have this evaluation board. I asked our team to assemble it for this video. Nothing special here. We see 3 LEDs and the battery, so the board can operate autonomously. There are also inputs for my photosensor. We'll connect it a bit later. These are the inputs. So I'm disconnecting the USB cable for now and placing the Portenta onto the evaluation board. Done. Now I connect the battery. Ready. Next, we'll upload a new program to our microcontroller, but first we need to remap the pins. According to my reference, the LEDs on the evaluation board are connected to pins 10, 11, and 12. And I update the numbers here and save it. Don't forget to press the reset button to activate bootable mode. Yes, now we can clearly hear that boot mode is enabled. And I launch my compiler. As you can see, the 3 LEDs on the evaluation board have started blinking. This means, as real engineers would say, we have successfully flashed the board. Now, let's test how our photo sensor works together with the microcontroller. I also wanted to show you a closer image. Here's our evaluation board. After inserting the Portenta, we press the reset button. It's located right here. I've circled it in red for you. And in this photo, you can clearly see the photo sensor connected. Now we'll test how it works together with our microcontroller. I'll connect it to the evaluation board as well, exactly as shown in the picture. Okay, I know the photo sensor is connected to analog input A0. I'll close the LED blink program, and now I open my next sketch, analog. Here I'm going to extend my block diagram. I designed the algorithm so that as soon as the light hitting the photosensor exceeds 450, the blue LED turns on. I also decided to add the green and red LEDs and set their trigger levels to 500 and 550. In this case, I'm choosing these thresholds empirically because I don't actually know what the exact limits should be. For my purposes right now, these values are symbolic. I will add 2 more settings for the red and green LEDs and the corresponding digital write functions. Before downloading to the microcontroller, I put my Portenta into bootable mode by pressing the reset button. Now in the program, I click compile and download. The program is loaded. Let's test how it works. I disconnect the USB cable from the Portenta and bring the flashlight closer. Yes, it works. Depending on the light level, my LEDs turn on. Of course, I created very basic demo programs, but using the functions I showed earlier, we can build virtually any logic, applying different mathematical operations and connecting various peripherals to our Portenta: LCD displays, serial devices, I2C devices, high-speed amplifiers, and much more. If you're interested in a specific application, write in the comments. We can explore it. We'll continue connecting different peripherals to our database tool program, and for today, that's it for Portenta H7, though we may come back later to it. Now let's briefly touch on our next task, creating an AI assistant that will help us work with our database tool. First, of course, I closed all the windows. We won't need them anymore. Now I'm opening my executable program, which I'll use as the foundation for building our artificial intelligence. Here we will apply a mathematical model. As a basis, we will use the Markov theorem, the so-called Markov chain. In very simple terms, if it's even possible to simplify such a major theorem, I'll try. Suppose we have a task and need to find the optimal solution. This theorem states that there are many possible solutions and each one follows from the previous state. At the same time, there is no backward dependency. If you're interested in the full model, write in the comments and we can talk about it in more detail. For now, let's look at how AI creation works in practice. I will use voice commands. Each voice command will trigger some background action, and each step of that execution will have its own tags. Think of them as keys that open certain doors, or in programming terms, execute specific logical tasks. We will also apply machine learning here. What does that mean in this context? It means the system will self-learn by recording correct decisions into dedicated memory segments and later reuse those successful outcomes when handling similar tasks. So let's begin the training process, the very beginning of our artificial intelligence. I'm launching my program called LaPlanda Player, and with its help, I will start communicating with my system. Now I'm putting on my headset with a microphone. The mic is currently turned off. I've already opened the library I created for training and I'm about to start communicating with the computer. I'll explain the purpose of this interaction later. Hello, LaPlanda.
Hi, I'm here.
Open database tool.
I don't know how to use the database tool. Do you want to train me?
I'd like to train you.
Good, I'm ready.
We will start with the basics.
I'm ready to learn the basics.
Learn database principles.
I'm loading the database principles. What kind of database provider you'd like to use?
Microsoft Access.
I have this information about Microsoft Access. Microsoft Access is a relational database management system, RDBMS, developed by Microsoft. It's part of the Microsoft 365 suite and is designed to help users create and manage databases for various purposes, from personal projects to business applications.
You know this?
Yes, I know all about MS Access databases and have been created by humans throughout their history.
It is something new to learn.
Great, I'm always ready to learn something new.
Let's continue next time.
I really wanted to learn something new today, but if you decided to continue next time, I'll be waiting.
Well, we can consider the initial training of my AI assistant successful. There is still a lot of work ahead. Of course, it will take much more time to perfect my assistant robot. How everything works in the background, what tasks are being executed, how we will enrich our AI with intelligence, and how our machine will interact with the external world, not just at the dialogue level. We will cover all of this in future episodes. And that's all I've got for today. Thank you for joining LaPlanda Tech. If you have any questions, please leave them in the comments. If you learned something new today, give this video a like and subscribe to learn more from upcoming episodes.